Greetings, aspiring scientists. Welcome to my video today. Taking a short break from making the syllabus content. Had some requests to make some guides for paper 1B specifically. So I'm going to try that today. Maybe try to help some people who are about to do their May exams. A lot of people find paper 1B to be either the most difficult or the most difficult to understand and learn how to study for. So I'm going to try to give my advice and go through a whole paper. First of all, let's just go to some posts I made on Reddit here recently. So I've seen like at least once a week maybe people post this. Does anyone have tips on how to solve chemistry paper 1B or physics or biology paper 1B? Feels like I'm literally guessing the whole time and hoping for the best. How can I study for it in practice? So I'll go through some of my answers to these. First, what I say, the best thing you can do is look at past papers, obviously. They give a lot of information and help you prepare exactly how to study for what's upcoming. What's upcoming will be very similar to what has been. Also, the tools section of the subject guide, the new 2025 guide, and in textbooks, like I use the Oxford Course Companion, so it's the yellow section in the middle labeled tools. Those are really what will mainly be tested on paper 1B. And beyond that, it's just a lot of experimental methods and things that you would and should do in lab work and lab reports while you're studying in IB science classes. So if you can find methods and lab reports that are very detailed and done by good teachers, those are extremely valuable. They might not come from the teachers at your particular school, but if you ask around for, what your friends in other schools are doing, or just check online what's been posted publicly, you might find some good examples. And then there are patterns in the techniques and experimental knowledge that are most often tested. Like there's a lot of titration, there's a lot of colorimetry, there's a lot of making solutions, that kind of thing. Those ones that appear over and over and over in past papers, you should study in detail. So a few things off the top of my head: how to prepare a standard solution, how to use volumetric flask, how to get delta T from calorimetry, temperature versus time graph, etc. I could go on forever. There's many, many things. But those are just what came to my mind as some examples. Then I say you can also check out this comment I made a while ago. So a couple months before that, I think I also made another summary. So there's no official really list of what will be on paper 1B other than it focuses on the tools section of the subject guide. But one good thing you can do is look at what experiments used to be required before the 2025 syllabus. So there used to be like determination of the empirical formula of something, usually magnesium oxide. There was titration using NaOH and HCl. There was determination of molar mass of an ideal gas. There's a list of about 10 experiments, I think, that either were required or that most teachers very often did. And those kind of give you hints on the skills that are still required these days, even though they're not completely mandatory to do any experiments like that anymore. They still appear on the paper 1B section. Okay, so paper 1B things are more related to lab work and lab reports that we are supposed to be doing. So oftentimes people who have done good lab work throughout the 2 years of the DP program actually don't have that much problem with paper 1B, I think, because they've been in the lab every week or every 2 weeks making solutions, checking errors, using a bunch of all these instruments. But it's the people who have only been a couple times to the lab. I've seen some classes that only go a few times, and they start to struggle. They may have only done things once, don't remember it, or maybe didn't do it at all, or maybe did it through simulations. Like with AI, I've seen some classes do it as well. It doesn't really prepare you to answer questions about what someone should actually do in the laboratory. So if you don't get the experience you need at your school, look up what is done at other schools as much as possible and try to see what it's like to write a really good lab report. Then here's my advice. master experimental uncertainties. There's almost always one or two questions with varying difficulty, but they'll almost always involve a multiplication or division that requires you to add some relative uncertainties, some fractional uncertainties. If you need help with that, I made some very good videos on it earlier on my channel. So know how to get uncertainties from analog or digital instruments. Very often they'll show a picture and say, what would the measurement be here with its uncertainty? Know how to get it from a collection of data. So you can take the average and find the range to get the value and its uncertainty. Know how to propagate uncertainties through additions. Add the uncertainties together. Additions and subtractions, same rule. Then for divisions, multiplications, and powers, get the relative uncertainties and add them together. Know how to reduce your uncertainties. Often it's a question like, how could this person reduce their uncertainties and, random and systematic errors? Think about how you would do that in pretty much any situation. There's always things you might be able to do. Next, number 2, master graphs. So know how to read and set up your graph with an x-axis, y-axis, how to label them, title the whole graph, write units, choose or set up good gradations. That's like the space between squares or lines. How to use scientific notation, and oftentimes graphs will have something written in scientific notation on the axis. You need to know how to transfer that into the equations you might be using. I see a lot of mistakes made there, transferring the scientific notation and the units that are written on an axis correctly into an equation where they might be used. Know how to plot points and draw error bars around them. So the error bars are the uncertainty, usually a plus or minus section. So if you have that on the x-axis and y-axis, you'll end up drawing a zone of uncertainty. Again, these things are in my uncertainty video if you're interested. Know how to find the equation of a straight line, definitely. You'll have to do this for lines of best fit, for tangent lines, for like initial and instantaneous rates, for example. So slope of a line, choose 2 points, then y2 minus y1 over x2 minus x1. Definitely know how to do that. Then master errors. Number 3, you should know the difference between systematic and random error. Familiarize yourself with many examples of both. So for all the experiments that I mentioned at the beginning of this video, think about what kind of errors are most likely to happen there. Systematic and random. Know how to identify and reduce errors, just like uncertainties. Don't really use human error as an example. You can't say, well, maybe these results are all off because the person, just didn't do it right or made a mistake or dropped something, Sometimes answers are borderline, like human error, or they might be acceptable to answer IB exams, but most of the time, you should give very specific examples in the method or things that maybe escape the method that were not talked about, instead of just saying the person messed up, okay? In paper 1, we're generally supposed to assume the student followed a given method correctly. It's problems with the method that we are trying to identify. Then number 4, master common lab instruments. In science, we often need to measure sort of like at least the base I units and some base SI units and some other ones. So length, time, temperature, mass, concentration, and other amounts. So know a good instrument to measure these things. It's more on the physics paper 1B exams where you'll be maybe asked about large scale versus small scale things. So in chemistry, I'd say mainly just know one good instrument to measure these things. And then for the volume ones, you have various volumes like 100 milliliter, 10 milliliter, 500 milliliter. Just make sure you choose a good one for the application that you're making. Like if you have to make 5 100 milliliter solutions in the end, don't choose something like a 10 milliliter beaker or something that's gonna not make enough total. And then, okay, even with all that, people who do well on paper 1B just have good common sense, math, intuition, graph reading, and drawing skills. It's kind of true. But you can improve these just by trying past papers and make sure you check the mark scheme and that you're doing everything right. Okay, so let's go to some practice slides I've been making. So I've taken a bunch of questions here from a previous past paper from the new 2025 syllabus, but I've just changed some numbers and names here and there because I'm a little bit worried about copyright infringement. But overall, the structure of these questions is exactly the same as a recent paper 1B. Excuse me. So let's get started. Number 1, the concentration of magnesium Mg2+ ions in aqueous solution can be determined by titration with ethylene diamine tetraacetic acid, EDTA, or by atomic absorption spectroscopy. The EDTA must be standardized by titrating it with a standard solution of magnesium chloride. An accurately weighed mass of powdered magnesium carbonate was dissolved in concentrated hydrochloric acid and heated up to remove all CO2. After cooling, the magnesium chloride was made up to exactly 500 centimeter cubed. Okay, so right away you just get a bunch of information about an experiment that someone's doing. This is fairly common. And the questions might start easy, so state the most appropriate glassware to make 500 centimeters cubed of Mg2+ solution. So we need to make a solution that is exactly 500 centimeters cubed, that's 500 milliliters. And if you've studied solutions and concentrations and gone to the lab and worked with glassware, hopefully you've learned that there are several types of glassware you can use. There are beakers, there are volumetric flasks, there are graduated cylinders. But in this case, when you are making a solution of a set volume for a standard solution, the best choice is the volumetric flask that is exactly this size, that has a line on it that will directly identify when you filled it to 500 centimeters cubed. So 500 centimeter cubed volumetric flask. It's really the only answer here. Beakers are too inaccurate. You'd probably only get 1 or 2 significant figures here, whereas we need to have 4 here, 4 significant figures. So that's just something you need to get used to by working with glassware in the lab. Okay, so then part 2, describe the steps that should be used to dilute the magnesium chloride solution to 500 centimeters cubed. So I'm going to be typing this. I don't want to write all this with my pen. So there are some specific things I think you need to mention where if you don't do these specific things, you might introduce problems like spilling or improper mixing or overshooting or undershooting. So I'd say using a funnel, pour the correct amount. We don't have any numbers really yet other than the size of the final flask. So this person, we assume, measures the correct amount, calculates the correct amount that they need, and we'll just talk about the correct amount here. So pour the correct amount of magnesium chloride solution into the volumetric flask. Better be specific, the 500 centimeter cubed volumetric flask. Okay, next I'd say rinse your MgCl2 transfer vessel, whether it's a graduated cylinder or pipette or whatever. It needs to be rinsed with DI water, distilled or deionized water. and transfer that water into the 500 centimeter cubed flask as well. If you don't do this, you're going to be undershooting your concentration because you haven't properly rinsed and added all of the MgCl2 that you calculated that you needed. Right, after that, fill the 500 centimeter cubed flask to the line. There'll be one line on it that just represents a full volume of 500 centimeters cubed. It needs to be with DI water. Okay, so then your volume and concentration should be good. The problem is it's not mixed well and there may be some transferred solution stuck on the walls. So I think the final thing you need to do is invert and mix the contents of the flask several times, maybe 3 times. Okay, that should be good. So I think those steps are required to answer this properly. If that's new to you, well, this is a good chance to learn how to use a volumetric flask to make a solution. Very commonly on exams, and it should be in the tools section of most textbooks. Okay, what's next? 1B. Okay, magnesium chloride is not used to make the standard solution because it readily absorbs water. Suggest how magnesium chloride could be treated in the laboratory to remove all absorbed water. So even if you haven't done this before, if you think about it, you might come up with some good answers. I think there's 2 acceptable answers on an IB exam. One of them is to place the MgCl2 solid in an oven to dry it. If it's absorbing water, we need to make sure all the water is removed, and heating it with an oven will cause the water to vaporize and leave. But it must maintain a constant mass. That's how you know when it's done. And if you just do that once, that might be an error, so it's good to do it twice. You know, put it in the oven for an hour or so, check it out, check the mass before and after. If there's no change, you know no more water is being removed. So do it for 1 more hour after that. Then you can pretty safely say any significant amounts of water will be removed. The other option is store it when it's not being used in a vacuum desiccator. This is kind of a special storage instrument that constantly has a vacuum in it and will pull out volatile substances, including water. As long as it's stored in there at least for a day, you know, ideally you'd want to store this whenever it's not being used. Okay. Next, 1C, a sample of tap water was titrated against a standardized EDTA solution using Aerichrome black T as an indicator. I've never heard of such an indicator, but probably behaves like any other indicators, like phenolphthalein. Following data were obtained. So we've got final burette readings, initial burette readings, and the volume added, which will just be the difference between final and initial. Final minus initial. 4 trials. And then the question suggests 2 reasons why the volume added in trial 1 was much larger than the other trials. So again, if you've done titration 2 or 3 times and then again in your IA, you probably know how to answer this very well. But if you've only done it once, or maybe never, you've only read about it, I think answering this would be very difficult. But if you think about it, you might come up with some good answers. So one thing that is often done in titrations is when you're adding drop by drop, adding 25 milliliters can take a long time. It can take all day. So you want to get near that 24 milliliter volume that you're going to add, maybe get to 20 or 22, and then start going slow. But to even know that your target is around 25 or 24 here, oftentimes people in their first trial will just go fast. So the researcher or the student may have gone quickly in trial 1 to estimate the volume that will be needed. So they maybe didn't even intend to use trial 1 as real data. Just for speed, the purpose of speed, they do trial 1 quickly to see that it's around 25. Then next time they'll go quickly to 20 or 22 and then start going slowly. Another reason, there's a lot of things you have to do to set up a titration properly, and one of them is to rinse and then completely fill the burette, including its tip. So the researcher may not have completely filled the burette's tip, especially with EDTA solution. Which led to an overestimation of the volume. Because you got to think about what you're saying here. Does it make sense to these results? So if the burette tip had an empty bit of air in it, well, now your solution above needs to fall into there, so the reading will go down above. And then you would actually start losing your solution to do the titration. So it's going to look like you used a bit extra volume than you did. So I think these are the two main reasons I would suggest. Other possible answers are that the burette was not rinsed properly. Maybe there was contaminants or DI water from when it was washed before. These things can affect the volume that would be calculated here as well. But these are the two main ones I think I would say. All right, so same data here, part 2, state the name given to a value that differs significantly from the others. This is kind of a statistical name, but you need to know it's called an outlier. There are a couple other acceptable answers, I think, like non-concordant. Concordant is like meaning in agreement with each other, and for titrations, it's usually within 0.1 milliliter of the other readings. So trial 1 would be non-concordant. It's like almost 1 milliliter difference. But 2, 3, and 4 are concordant with each other. They are within 0.1 of the trial 4, for example. But just saying outlier is enough. Next, suggest a reason why trial 1 should not be included when finding the mean volume of EDTA used. So one of the next steps that this researcher would do is to find the average volume added and then move on from there. But if they include trial 1, it's going to be a lot higher than if they excluded it. Because trial 1 is an outlier, so part 2 is kind of leading you into the answer to this. And non-concordant with the other trials. 2, 3, 4. So if it is included, the average will be too high due to systematic error. So again, the reason might be that they went quickly to guess the amount of volume in trial 1, or maybe they left the air on the tip, those reasons that we discussed previously. But in any case, it is a systematic error where it's too high. So you don't want to include it. All right, next part 4, calculate the percentage uncertainty in the volume of EDTA used in trial 2. So, the uncertainty in this case will be the uncertainty of the burette readings added together. Since we're doing a subtraction, final minus initial, then we know the absolute uncertainty, delta V, is equal to the final burette reading uncertainty, 0.05 centimeter cubed, plus, even though it's a subtraction, the rule for propagating uncertainties through subtraction is to add them together. So plus the other burette reading is also 0.05, so this ends up being 0.10 centimeter cubed. This is not the answer though. We are supposed to find the percentage uncertainty. So for trial 2, the actual volume added was 24.35. So delta V over V for trial 2 is equal to 0.10 centimeter cubed divided by the volume added for trial 2, total volume added, 24.35. So this ends up being about 0.0041 or 0.41% uncertainty in that calculation, calculated value. So again, if you need uncertainty practice, go check out one of my other videos. That's all for this. Now, part 5 of C, the endpoint of titration is when a red complex A changes to a blue ion B. Explain how this shows that A absorbs radiation with higher energy than B. Okay, so this is more of a theoretical thing, where if you've studied electron transitions and transition metal complexes and ions and how they interact with light and colors, you'll be able to answer this very well. But here's what I would say. So the color observed is the opposite of the color absorbed. This is something you have to realize. Whatever we see with our eyes is the opposite. It's sort of what is reflected or not absorbed by the actual chemicals, molecules, ions, and atoms. So if red is observed for A, then green light is absorbed by A. And that is, about 550 nanometers. You can see this from the data book. There is a color wheel in there. So the wheel has sections with different colors in it. Whatever is on the opposite side of one color on the wheel is its opposite color. So opposite of red is green. Conversely, if blue is observed for B, then orange is absorbed, that's the opposite color. By B. And that wavelength is about 600 nanometer. So 600 is greater than 500, and energy is proportional or inversely proportional to wavelength. So A must absorb higher energy. A has the shorter wavelength being absorbed. Shorter wavelength means higher energy radiation. I think that's the good way to answer this question. Maybe you don't need to be so wordy or in detail, but I think you do need to identify the opposite colors, the wavelength difference, and the proportionality between wavelength and energy. Good. Next, D here, a standard stock solution of magnesium chloride was diluted to produce several solutions with accurately known concentrations. The absorbance of each was then measured with a spectrophotometer, which was calibrated with distilled water. Draw the line of best fit on the graph. I guess I'll give it a shot, but you can see that this is quite clearly a linear relationship, as it should be, because absorbance with concentration is almost always linear. So you need a line that approximates this straight line, but these points will not exactly form a straight line just due to some error. So you need to try to get, anytime one point is slightly above the line, there should be another point balancing out that, slightly below the line. So I'll try to draw that. Okay, I didn't do the best job here, but you can see, whereas this line is a little bit above it, this line is a little bit below it. If I drew it really well, those sort of distances would be equal. Just very hard to do with this pen I'm using. But the bottom point and the top point are essentially on the line, which is good. Then we have another point slightly above, another point slightly below. This will lead to a good average line. And this should be a straight line. What I've drawn here looks a little bit curved, I can see. But just do your best. And determine the concentration in ppm of Mg2 plus ions in a sample of tap water with an absorbance of 0.05. Okay, so you need that line of best fit that I drew before. I'll try to draw it again. A little bit better that time, maybe? Straighter. So if that's your line of best fit, how can we get the concentration of Mg2 plus ion in a sample of tap water with absorbance 0.05? So your absorbance, 0.05, is here. Look across where this intersects your line of best fit. So that looks to be just above 5 ppm, right? So I'd say, what can I write? Like, C is approximately equal to 5.1 ppm. Based on this line of best fit and this data. But generally the answer will have a range here for what is acceptable. I don't think a range was given in this mark scheme I was looking at, but as long as you're close to this, like plus or minus 0.5 maybe ppm, could be okay. Okay, next. So this is the actual equation for absorbance. Absorbance equals log base 10 of I naught over I, where A is absorbance, I naught is the intensity of the incident light, and I is the intensity of light which has passed through the sample. Determine the percentage of incident radiation that is absorbed by a sample with 0.090 absorbance. Okay, pretty tough. Even to understand what this is asking, it's asking several things and giving you several pieces of information. But it's really important to determine what this is asking for first. So determine the percentage of incident radiation that is absorbed. So is that I naught over I? I naught is the intensity of incident light, and I is the intensity of light which has passed through the sample. So I naught over I actually does not represent the percentage of incident radiation that is absorbed, because I naught will be higher. If the light is absorbed as it passes through, I should be lower than I, so this will give you like over 100%. It's not this that you're trying to find, it's maybe the inverse of this. I over I naught. So I is what passes through, I naught is what you started with. I will be lower than I naught. So this will give you some percentage less than 100% for what passed through. So that's a good point. This will give you what passes through, but this question is asking you for the percent absorbed. So what you actually want to find is the remaining percent from that number. 1 minus I over I naught. So you might be asking, how could I know that? And the only thing I have to say is practice, percentages, inverses, ratios. You have to be a master of these things to really do well on IB exams for chemistry and physics especially. So we want to find that 1 minus I over I naught value. That means we are going to have to find I naught over I. So can we arrange this equation in any different way? We can maybe raise both sides to the power of 10. So 10 to the power of the absorbance equals 10 to the power of log 10 will cause that to disappear. So this should just be equal to I naught over I. All right. So we'll have our absorbance of 0.090. 10 to the power of 0.090. Okay, 10 to the 0.090 ends up being about 1.23. So that is I naught over I. But we instead would like to find I over I naught for that final equation. So we need to take the inverse. Inverse is 1 over the number, 1.23. So this is about 0.8128. Okay. Now we'll put that in this equation. So 1 minus I over I naught. 1 minus 0.8128. So this will be about 0.187 or 18%. I think the significant figures can get a little bit difficult to put through here, but 3 I think is fine here. All right, so that's how I would recommend that you do this. Not that easy, but this type of equation will appear in physics as well with sound. All right, let's move on. So the 8 ppm solution was made by diluting 4 centimeter cubed of stock solution to 25 centimeters cubed. Calculate the concentration in ppm of the stock solution. So this is a dilution. You really should have done practice questions with this and done it in the laboratory before you write paper 1B. But there's an equation you can use. N before equals N after. N1 equals N2. This will be written usually as C1 V1, since N equals C times V, equals C2 V2. And we would like to know C1. So C1 equals C2 V2 all over V1. So final concentration is 8 ppm. Then final volume is 25. I can keep this as 25 because it would just be a ratio between centimeters cubed. Over V1, that's the amount that was taken out of the stock solution. That's 4 centimeter cubed. So this comes out to be 50 ppm. Stock solution must have been 50 ppm. .0, keep your 3 sig figs. Next. Calculate the concentration in mole per decimeter cubed of Mg2 plus in the 8 ppm solution. Keep in mind 1 ppm equals 1 milligram per decimeter cubed. All right, so this just tests your dimensional analysis skills and ability. That's something else I should have mentioned that's really important for paper 1B. So we've got 8 ppm. Then we have a conversion factor, 1 ppm equals 1 milligram per decimeter cubed. So this equals 8 milligram per decimeter cubed. We need this to be mole per decimeter cubed. So I'm going to recommend that you change milligrams into grams. To do that, multiply by the conversion factor for grams, 1 gram per 1,000 milligram. So we'll end up dividing 8 by 1,000 to eliminate these units of milligrams. And then we need to change grams into moles. We do have a way to do that with the molar mass. Molar mass of magnesium is 24.30. So we'll multiply this by 1 mole per 24.305, I think, gram of magnesium. This way our gram units will cancel out. We will be left with mole per decimeter cubed, hopefully. So this comes out to 3.29 times 10 to the minus 4. Mole per decimeter cubed units. Done there. Okay, even if you've never done this before, you'll often have to transform between units you might not have seen before. You should be ready for that, doing this dimensional analysis using conversion factors. Next, spinach leaves, number 2, were boiled for differing amounts of time. The water was cooled and tested for the presence of iron 2 plus ions by titration with potassium permanganate 7 solution KMnO4 aqueous. 3 trials were done for each boiling time. In each trial, 5 grams of spinach was boiled in a beaker containing 250 centimeters cubed of tap water for 5, 10, 15, and 20 minutes. Spinach was separated by filtration, and the solution was bottled and stored in a refrigerator until titration was performed. State the dependent and independent variables. Okay, so very important. Okay, so the independent variable, this is what you will set up and control yourself. This person clearly states they're going to be setting boiling time to 5, 10, 15, and 20 minutes. So that is their independent variable. Now their dependent variable is what depends on that boiling time, or so they think. But you got to be careful. It's not what they're eventually going to calculate. It's like exactly what they measure in the laboratory that will be changing. So in this case, they're doing titration. So it will be the volume of the titrant which is in this case KMNO4, solution used to reach the endpoint. Okay, so they will eventually convert that into the iron 2 plus amount, but before the calculation, they measure this in the lab. That must be labeled as the dependent variable. Okay, moving on. Suggest 2 experimental conditions that should be controlled to ensure that the methodology is valid. So even though they will not be using some other things as their independent variable, they still need to control their experimental setup to make sure that any relationship is between the independent variable and the dependent variable. So there's many things that they could do. The main one that I was thinking of is the Spinach source. Needs to be kind of constant, meaning size, freshness, brand or shop that they got it from, and so on. You should try to make the spinach as similar to each other as possible, spinach leaves. Other than that, I think storage time is pretty important. You know, if you do one on one day and then one a week later when it's been sitting in the refrigerator for a week, you could easily get different results that's not due to your boiling time. Those are the 2 that I would say. But I think there are some other ones that are acceptable, like that were mentioned in the mark scheme. Remove stems. I don't really know why that's so important. What else? Boil water before use. What else? Consistent storage bottles. So not just the storage time, but the containers that they're in, make sure that they are similar to each other. And this could go on and on. As long as you do have a reasonable idea, it probably will be accepted. Things that you can control. Oftentimes my students always write temperature. It's like, kind of yeah, but I think that answer will actually not be accepted because it's so general, and a couple of degrees here and there probably would not affect the results of this particular experiment. Okay, next, part 3, suggest an additional step that should be performed to determine how much iron 2 plus was extracted only from spinach leaves. So this experiment should be done with tap water itself. So, you know, you can boil it, titrate it, and see how much iron 2 plus might be in the tap water alone. That way, you know, any additional amount is actually from the spinach leaves. So, perform this experiment with tap water itself first. So any additional Fe2 plus beyond that amount can likely be attributed to the spinach leaves. Themselves. Okay. Next, suggest 2 difficulties that the student might encounter when determining the endpoint of this titration. So if you've actually done this experiment, I've had a couple students do their IAs or EEs with spinach titration with KMNO4, and it is very difficult to determine the endpoint. Why is it? If you haven't done it, it's probably very difficult to answer this, but think about it. Spinach contains a lot of different pigments, especially green and kind of browny. So when it is boiled, all those pigments enter the water. So its mixed colors are difficult to distinguish. You're looking for a kind of endpoint where the permanganate disappears and becomes either colorless or like pale yellow, but it's going to be mixed with green brown from spinach. So it's difficult to identify. What else? So one of the main things is that potassium permanganate solution is very dark. This is just something you should start to be aware of. Permanganate is an oxidizer used in so many chemical reactions that it's very often used, and we'll have to use it with glassware. So because it's so dark, it makes the gradations or the lines on glassware difficult to read. So readings cannot easily be taken below the meniscus, for example. So usually we have that kind of curved section in a water sample that's in a graduated cylinder or a burette. We would read the reading below, but all the numbers and lines are covered by this dark purple solution here. So we often have to read at the top of the meniscus, which will introduce some increased values, some systematic error there. All right. Other things are acceptable as well, like the whole reaction is time sensitive, so you want to do it as quickly as possible, but then the actual reaction, when you drop the permanganate into your solution, can take a lot of time to stabilize the color. So you're trying to wait, but you're trying to hurry, and overall it's just difficult. All right, moving on. So the average results were graphed here. 4 points for the 4 boiling time data points. State the relationship between the amount of Fe2 released from the spinach and the boiling time. So what relationship would you say? It's like either a horizontal line or a slight dip in it, but the answer is no relationship is visible. Don't write in all caps, but I'm just trying to emphasize it here. You can't get any meaningful correlation, proportionality, whatever from this graph. You got 3 points that are basically horizontal, showing no change, and perhaps 1 outlier. So this experiment is kind of a fail. Person would have to go back and redesign this to get any meaningful results. So comment on the range and quantity of measurements in this investigation. So there's one thing that is good, which is that the times are representative of cooking times. Five, 10, 15, 20 minutes usually would be about how long you boil some vegetables, which is good. You always want to ask when you're selecting your range of independent variables, is this how someone would actually use this process or this reaction? In this case, it kind of is. But no relationship could be shown. So lower boiling times were likely necessary. Especially adding the spinach without boiling. So extracting from the spinach without boiling can tell you whether boiling has any effect at all, and that's really necessary. So you want a 0-second boiling time to compare. How did this start? Was boiling having any effect at all? Based on the data we have here, it's not having any effect, but it's possible that, boiling it for 5 seconds, 30 seconds, 1 minute is where a big jump up to this extraction amount happens. That's what this researcher needed to identify. Is there anything else worth saying? So more measurement points were probably needed. can say that. Okay, moving on. Evaluate with a reason whether or not the results support the hypothesis. No relationship was seen. So the hypothesis they had was above here. The original hypothesis was that a higher boiling time would lead to increased amount of iron 2+ extracted. No, the results do not support this hypothesis. But the hypothesis was also not disproven. Due to the boiling times that were selected, the range was just a bit too small. So further investigation is pretty much needed to go any further here. Part 2 then suggests one modification to the method that would make it more suitable for testing the hypothesis. So this is kind of the same as one of the previous answers, but the researcher needs to try to extract with regular tap water without boiling. And if a difference is seen between boiling and no boiling, they need to find the time scale where the difference occurs, right? The time scales that they chose, 5, 10, 15, 20, shows kind of the complete effects of boiling, maybe the total amount that can be extracted, but it doesn't show where the change between no boiling and complete boiling happens, which is what you would want to try to show in this kind of investigation where you're trying to prove a relationship between boiling time and amount extracted, where the difference occurs, something like that. So likely more boiling time points at lower time are required. Okay, next, question 3, the last one here. So the reaction of solid sodium hydrogen carbonate, NaHCO3 solid with hydrochloric acid HCl was investigated using a common mass of solid and a constant volume of different concentrations of acid. A data logger was used to measure the mass of the reaction mixture every 5 seconds. The results were graphed. Okay, we get this graph of the 3 situations of acid, and then determined by annotating the graph the initial rate of release of carbon dioxide in grams per second with the 1.5 mole per decimeter cubed HCl. So that's the bottom line. So this is not particularly difficult, but if you've studied rates and rate graphs, you should have practiced this before in class. The initial rate is at time 0, and we need to draw a line tangent to that point. I did this on a separate piece of paper before. I'll try to do it again here quickly. No, that was terrible. Very difficult for me to draw a straight line. Okay, I tried many times to draw a straight line with my pen here. Very difficult, but this section, at least at the top here, is straight. After that, you should not choose those points underneath, but you might choose some points like here and at time 0. You need to get the slope of the line between those 2 points. That will represent your initial rate of reaction. So take your 2 points, y2 minus y1 over x2 minus x1. I'll just use the values I used on a slightly different line I drew before. So I think I ended up using y2 as 7.2 grams and y1 as 8.8 This was over x2 minus x1. I used 1 second as x2 and then 0 seconds as x1. So that ends up giving about minus 1.6 grams per second. Keep in mind though that rates cannot be negative, so we need to take the absolute value of that. So these two lines on each side are the absolute value symbol. So this is 1.6 gram per second. Now checking the answer guide, the answer ended up being more than that. It was like 2 or 2.2 or something. These initial rates are almost always a larger slope than you imagine, than you calculate with your own tangent line. But generally I think there'll be a range like plus or minus 1 gram per second even. So hopefully my answer would be accepted, but if you ever are worried about this, go a little bit steeper, a little bit of a higher slope than you might think. All right. Next, suggest with a reason whether NaHCO3 or HCl was the limiting reagent in the reactions using 0.5 and 1.0 mole per decimeter cubed. Okay, let's try to answer this. Okay, so this really tests whether you understand limiting reagents or not. So the important thing here is if something is in excess, excess means extra, much extra, then changing its concentration should not affect the final amounts of the products produced, okay? It's the limiting reagent that affects the amounts of products produced. So you just need to look at these graphs and say, were equal amounts of gas released in each of these three amounts, these three trials. So this shows the mass of a reaction mixture. So whatever is lost is that CO2 that's being lost. But we're changing the amount of HCl. And the amount of mass lost is quite different each time. You know, one time it's about 1 gram, another time it's about 3 grams, another time 3.5 to 4 grams. It's different each time. So that means HCl is absolutely limiting. At least in the 0.5 and 1.0 cases. Changing the acid concentration leads to different amounts of products. Being produced. Okay, that's all you need to say. Limiting reactants affect how much product can be produced. If it was excess, then changing this HCl concentration would not be changing the final amounts produced in these graphs. All right. Next here, the theoretical mass of CO2 produced in a complete reaction with 1 mole per decimeter cubed is 4.3 grams. Determine from the graph the actual mass of CO2 produced. So you can look, each of the trials here starts at about 9 to 9.4 grams. And they'll finish wherever these lines become horizontal on the right side. So from my calculations, I get that this trial with 1 mole per decimeter cubed is about 3.3 grams, 3.35 maybe. And I think I got that from 9.1 grams starting point down to 5.8 grams. So that's about 3.3 CO2 produced. That's actual. So we'll compare that with theoretical in the next part of this question, I'm sure. 3.3. Next, now calculate that percent difference between theoretical and actual mass. So there is an equation that is, I'll show here. I think this equation is not in the data book, but something that you need to know. Okay, so that equation is percent difference, often written as percent error, is equal to theoretical minus actual all divided by theoretical amount. So in this case, our theoretical was 4.3 grams. We'll subtract the 3.3 that I calculated from the graph, divided by 4.3. So this ends up being about 0.221, which is about 22%, I think we can say. 22% difference. And then that's done. All right, I think it's near the end. So although the same mass of NaHCO3 and volume of HCl were used each time, the graphs began at slightly different points, suggest a source of this error. There could be many, many reasons for this, but one might be the balance the balance used to weigh was not wiped off or cleaned properly and then tared properly. Tearing is when you set it to 0, cleaned and tared properly, not zeroed properly. So that will cause any random garbage or debris that's left on there to increase the mass a little bit. What else? Well, you only need one source, so that would be enough, but other things could be different glassware being used that has slightly different masses. If you don't tear in between those as well, the glassware could be contaminated as well. What else? Could be time stop and start error. You have to hit a button usually to start and stop this. It's a bit of reaction error. Any of those I think would be fine, and any other reasonable ideas you have, probably fine as well. If you have any questions about it, leave it in the comment. I can consider what answers you might have. So that will be the end, I think. Yeah. So hopefully you got some insight on how to answer paper 1Bs. If you want to see more, I can maybe do more in the future, maybe near future. But other than that, I'll continue my syllabus lessons on enthalpy and heat capacity and things moving forward. That's all. See you next time.